Hi, my name's Dr. AJ Kumar, PhD. I want to get started talking about Greek mathematics. Been wanting to do this for a while, and why not just start? Um, First theorem. So we're gonna really just be doing a deep dive into the history of math. So the first theorem ever discovered was the Pythagorean theorem, and I believe the context for this was you want to construct right angles. That was the idea. So what you would do is there would be a list of these so-called these are called Pythagorean triples. So most people learn that if you have a right triangle with side lengths a, b, and c, then it is true that a squared plus b squared equals c squared. Okay? It is also true, the converse of that is also true, which is that if you have three numbers a, b, and c, such that a squared plus b squared equals c squared, when you arrange them if you take side lengths, if you take those as side lengths and arrange them into a triangle, then that triangle will be a right triangle. Um, so that was the earliest sort of what we would call a mathematical discovery. What is obviously something abstract, something where we recognize that there is a property. Property. Not only did they recognize this property, but they also had a procedure for generating Pythagorean triples, which we'll talk about. It's actually not hard. Okay. Okay. All you need actually here's the procedure. Um, I'll just tell you the answer. Um, if you have a proportion, okay, and what would it be? I think it'd be 1 minus t squared over, wow, 1 minus t squared to 2t to 1 plus t squared. Okay. And I think if you let t be a rational and you take this proportion, it is true that this squared plus this squared equals this squared. Let's just try it. 1 minus t squared squared plus 2t squared. What is this going to be equal to? This is going to be, this first one, it'd be 1 squared minus 2t, 1 squared, 2t squared, I guess, yeah, minus 2t squared, yeah, plus t to the fourth, plus 4t squared, which is, of course, t to the fourth plus 2t squared plus 1 squared. And I can already tell you that if you expand that, you'll get the exact same thing. If you take this is equal to 1 plus t squared squared. If you expand that out, if you expand this out, you'll get this. Okay. And so if you let t be any fraction, then there you've got you've got literally every Pythagorean triple, by the way, is of that format. Um, we'll talk about that. So anyway, kind of really, I guess the towering figure of Greek mathematics, if we're gonna pick one, would be a guy named Euclid. The other, yeah, there's kind of two other candidates, Archimedes and Apollonius, but uh, I think Euclid is probably the towering figure of ancient Greek mathematics, and he wrote a book called The Elements, which is probably the second most important book in history, uh, behind the Bible, just in terms of influence. And there's this wonderful website that was written in it says copyright 1998, and wants me to have Java enabled. So it's a pretty old website, but it's excellent. It's got all sorts. It's the book Euclid's Elements is in the public domain. I have a Dead Tree version, um, and there's also Let me just make sure the recording is correct. Yeah, it is. Okay. Anyway, let's just start. Let's just get started with book one. And so there's what, 13 books. Actually, let's look at the table of contents again. Table of contents. Okay. So there's this pre-matter, which is his stuff. Book one, which is the fundamentals of geometry, theories of triangles, parallels, and area. Book two is geometric algebra. Book three is the theory of circles. Book four, constructions for inscribed and circumscribed figures. Theory of abstract proportions is book five. Book six, similar figures and proportions in geometry. Book seven, fundamentals in number theory. Book eight, continued proportions in number theory. Book nine, number theory. 10, classification of incommensurables. Book 11, solid geometry. Book 12, measurement of figures. And book 13, which is regular solids. And so I'm not sure what I'll do. Maybe I'll have the Greek math all be one playlist. I don't know. I think probably each book will get its own playlist. So I think this will be Euclid's Elements, video one. And we're starting with book one, and I think we'll read the definition. This is this book is important in a sense because it sort of is the founding text of mathematics. In the sense that this is where mathematics comes from. This is where the modern idea that you start with very clear definitions, you start with very clear assumptions, and you proceed by deriving things that are inescapable consequences of your assumptions. So we talk about and I'm also going to be doing stuff with GeoGebra, and I'll remember to, so Greek geometry, they don't have axes, they don't have a grid, they don't have any of that gay shit like coordinates. So we can talk about a point. Okay, a point is not meant, it's not like a filled in circle. The filled in circle is a diagram that represents that somehow we have this space that is made of points. It's zero dimensional. That's what a point is. I don't like this in my Math for Programmers. I'm going to talk about a superior way to think about points. But the Greek way is there is just this notion of a point out there. What is a line? This is curious. So here's what a thing you can do. So if we click definition one, yeah, he starts. Right. So, guide. The Elements is a prime example of an axiomatic system. So CIA math is axiomatic. And Euclid was really the guy who puts the axiomatic system, really gives the axiomatic system its legs. The CIA kind of cocks it up in the 20th century. But this is sort of seen as the obviously right way to do mathematics. I'm not sure axiomatics is the right way to do math. I don't think it is, actually. And so my fork of math, QAnal, is not axiomatic. Anyway, says the Elements is the prime example of we actually understand what a point is. You're welcome to go read this, by the way. I'm not gonna. I want to get through it. And I want to talk about what a line is. So this is curious because the terminology differs. Today we think of a line. So let's say I have 2 points. I think of a line as extending infinitely. And it's a straight line. So point is one of our primitives. Line is one of our primitives. So it's breadthless length. So it's one dimensional. It doesn't have as length. It won't have breadth. Whatever that means. It says it doesn't define. They're not defined what it means in the element. So the Elements rewrites mathematics and geometry as sort of ultimately in terms of these primitive notions: point, line, breadth, and length, whatever that means. Right, so a surface is two-dimensional, a solid. Yeah, today we think about it in terms of dimensions. One cannot tell Yeah, so this is what was confusing me. Does a curve count as a line? What today we call a curve, but it seems like maybe. Yeah, today we might call them segment. Um, I guess, yeah, it does. One piece of terminology that Euclid did not mention explicitly in a definition is a phrase to indicate incidence, yeah, when a line passes through a point. That would be a primitive relation that would hold between a line and a point. Postulates would be included as well to give meaning of the right. Okay, that's interesting. Okay, ends of a line are points. Right. So he is thinking about it. We can, he's thinking about it as curves. Okay, a straight line lies evenly. That's unusual. Anyway, today we talk about a line segment. Okay, that's I think what he means by a straight line. Right, we can extend a straight line. That's interesting. Okay. Which is sort of like this concept of we can make a line that goes infinitely off in either direction, which is actually a profitable way to think about a line. Um, but I think the Greeks, especially Euclid, was very, very nervous about this concept of infinity. Um, anyway, a surface is that which has length and breadth only. Okay. The edges of a surface are lines, right? Okay. A plane surface is, okay, a surface that isn't curved. Okay. A plane angle is the inclination to one another of two lines in a plane. Okay, so maybe like he defines it as an inclination. I think today we would think about it's actually really, really difficult to talk about what a wedge is. Um, yeah, okay. So here we talk about an angle. Today we measure angles in degrees. Euclid does not measure angles, and that's actually a really important idea. So he has this idea that he can compare angles. He has a given angle which he calls has this idea of a right angle. So he knows about right angles. Which I didn't do a very good right angle there. That was pretty good, actually. A plane angle is the inclination to one another of two lines in a plane which meet one another and do not lie in a straight line. When the lines containing the angle are straight, the angle is called rectilinear. Ah, okay. So, right, we're forgetting that lines doesn't mean straight line. Okay. So let me, what I think he means is this idea that I can maybe have two curves. Okay, let me, anyway, I can have two curves and the curves meet at some sort of angle. Right, I think that's the idea. Two lines. Do not. What does this mean? I see. Angles do not have to have straight sides. They can have curves as sides. The so-called horn angle is described as an angle between a circle and a straight tangent line. Huh. That's interesting. Angle doesn't have an extent. I don't know. Okay, definition 9. What does rectilinear mean? Okay, so it's like not a horned angle. Okay, I think that's what it means. Okay. When a straight line standing on a straight line makes the adjacent angles equal to one another. Okay, what? Ah. Okay, this is defined as a right angle. Okay. Obtuse angle. Right, we can compare angles. We have a right angle. We can compare angles to figure out whether one is bigger than the other. We don't really have a measurement system in terms of degrees. Acute angle is one that's less than a right angle. A boundary is that which is an extremity of anything. A figure is that which is contained by any boundary or boundaries. A circle is a plane figure obtained from one such that the... What? Okay. A circle is a plane figure contained by one line such that all the straight lines falling upon it from one point among those lying within the figure. Right, okay, so straight... Right, okay, the boundary of the circle, or the circle itself is called a line, not a curve, such that all those straight... Ah, okay, I see. Okay. Shut up. Okay, here's the idea. Let me explain what this means. So let me make a circle. Okay. The idea here, what this means... Okay, I have my circle here. What this is saying is that if I make a segment that goes through the... Ah, okay. So what it's saying is I pick a point, and if I have radiuses, radii, I guess, it's sort of the locus of... I see. Okay, the circle is defined by something that has a fixed radius. By a figure that has a fixed radius and it has a center. Right, that's the center of the circle. Right, a diameter of the circle would be a line segment that... what the hell? Right, we know what a diameter of a circle is. Terminated in both directions, and such a straight line also bisects the bisects the circle. A semicircle, right, is half of a circle, and the center of the semicircle is the same as that of a circle. Okay. Right, okay, this makes more sense. Okay, we've done that. Rectilinear figures are those which are contained by straight lines. Trilateral figures are those contained by 3, quadrilateral those contained by 4, and multilateral those contained by more than 4 straight lines. Okay. Of trilateral figures, an equilateral triangle is that which has its 3 sides equal. An isosceles triangle is that which has 2 of its sides alone equal. And a scalene triangle is that which has its 3 sides unequal. All right, right. We remember equilateral, isosceles. I forgot scalene, but okay. Further, of the trilateral figures, right? So, for instance, if we take, let me just show you. If we take 2 points in the circle, then I always get isosceles triangles like this, right? Further, of trilateral figures, a right-angled triangle is that which has a right angle. An obtuse angled triangle is that which has an obtuse angle. And an acute triangle, right, is that which has its 3 angles acute, right? Of quadrilateral figures, a square is that which is both a quadrilateral and right-angled. And an oblong, that which is right-angled but not equilateral. A rhombus, that which is equilateral but not right-angled. And a rhomboid, that which has its opposite sides and angles equal to one another. Okay, well, let's start over. Square is both equilateral and right-angled. Oblong, an oblong, which today we call a rectangle, which is right-angled but not equilateral. Okay, that's what an oblong is. Rhombus is equilateral but not right-angled. Also like a parallelogram. Right, or like a diamond would work in that case. A parallelogram, I think. Let's look at this. So, square, rectangle, rhombus. Okay, trapezoid, I remember that. And E is a parallelogram. Okay, so a rhombus is like a... What's the difference between a rhombus and a parallelogram? I guess rhombus doesn't require parallelism? Okay, rhombus... Ah, all 4 sides are equal. I see. Right, so B is, if we're making a tree, a square... Here, let's make a table. Equilateral... right-angled, let's make a table. Okay. It's a square, which is both. Rectangle is not equilateral, but is right-angled. A rhombus is equilateral and is not right-angled. Okay. A rhomboid has opposite sides and angles equal to one another. So like a parallelogram. Right, okay. Ah, rhomboid. Okay. A rhomboid. So, if you imagine we took a square. Okay. Okay, here's our square. And imagine I apply like a shear to it. Okay, so it would look something a little bit more like this. And notice that there's like a I'm lowering it deliberately. So it's still equilateral, it's still equilateral, but now it has these opposite angles are equal. And my opposite sides are still obviously equal. This is a rhomboid. Okay. I'm going to have to get used to that. And then the other ones are trapezia or trapezoids in modern terminology. Okay. Parallel straight lines are straight lines which, being in the same plane and being produced indefinitely in both directions, do not meet one another in either direction. Okay. Let's talk about the postulates. Postulate 1, to draw a straight line from any point to any point. So this is saying we can make line segments. Okay. So typically Euclid's geometry is called ruler and compass construction. It's more accurately would be straight edge and compass construction. It's an unmarked ruler. So straight line from any point. If we have a straight line, we can extend it, it seems like. So I think what I'll do is, in those cases, do this. Okay. To describe a circle with any center and radius. Okay, we can do that in GeoGebra. Great. All right angles are equal to one another. Okay. And then this postulate 5, that if a straight line falling on two straight lines, right, this is really confusing. Let's look at this. That if a straight line falling on two straight lines makes the interior angles on the same side less than two right angles, the two straight lines, if produced indefinitely, meet on that side on which the angles less than the two... What? So he's defining parallel lines by this idea about... Let's read this. Should include the condition that the two straight lines lie in a plane. Otherwise skew line. Right, so if you have here, let me make a new one that's... Right, if we have in 3D space... God damn it. Fucking ridiculous. Okay. What I can do is I can make two lines that don't lie in any sort of plane with each other. And these technically, God damn it. How do I like pan? Right, these don't lie in any sort of plane with each other. That's what I think skew line. Okay. Right, so this is an example of where Euclid has hidden hypotheses. He has a lot of these, actually. It's still work of divine genius. These mistakes were not discovered until like the 20th century, I believe, or the end of the 18th century, 19th century, whatever. Right. Okay. If ABE plus BED, okay, we can add angles apparently, and if it's less than two right angles or 180 degrees, then these two lines, of course, will go meet somewhere. And if it's greater than 180 degrees, like over here, they'll meet on the other side. Okay. And if it's exactly 180 degrees, then they'll be... Yeah, okay. The parallel postulate is the most interesting historical postulate. Geometers throughout the ages have tried to show that it could be proved from the remaining postulates so that it wasn't necessary to assume it. The process tried was to assume its falsehood and then derive a contradiction. Many strange conclusions follow from denying the parallel postulate, and several geometers found such great absurdities that they concluded that the parallel postulate did follow from the rest. Nevertheless, these apparent that's interesting. These apparent absurdities are not contradictions. In the early 19th century, this is going to be fun when we get to this, Boilai, Lobachevsky, and Gauss found ways of dealing with this non-Euclidean geometry by means of analysis and accepted it as a valid kind of geometry, although very different from Euclidean geometry. This hyperbolic geometry, as it's called, is just as consistent as Euclidean geometry and has many uses, like physics. Thus, we know now that we must include the parallel postulate to derive Euclidean geometry. For more on non-Euclidean geometry, see the notes on hyperbolic geometry. That's interesting, after 1.29 and elliptic geometry after 1.16. Euclid does not use this parallel postulate until proposition 1.29, but nearly all the rest of Book 1 depends on it. For more commentary on the postulate, see guides to 1.29 and 1.30. Okay, those are the postulates. Common notions. Things which are equal the same thing also equal one another. Okay, so if A and B both equal C, then A equals B. Equals are added to equals, then the wholes are equal. If equals are subtracted from equals, then the remainders are equal. Things which coincide with one another equal one another. So there's this thing about what does equal mean? So equals in Greek geometry means there's a congruent symmetry, which means I can sort of pick something up, do some rigid motion to it, rotate it, maybe reflect it or something like that, and those are equal. So if a rigid motion, if I can get from A to B with a rigid motion, that's why I can compare angles. I can pick one angle up and put it on top of another angle and see if one's bigger than the other. I can maybe add them. Right, and the whole is greater than the part. Okay, I'm gonna stop here because I'm out of gas. Next time we'll get into the propositions. This is gonna be a lot of fun. All right, see ya.